Check. check. I have the slide.
Check, check, check. Check, check, check. Where do you want us to stand? Okay. Okay, we ready? Ready?
Hello? Check,
okay.
Check.
Can y'all hear me? No?
Hello?
Check, 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 check. Moon,
Check,
moon,
check.
moon, moon, moon.
Check 1, 2.
X-ray, X-ray, X-ray.
Chandra.
All right. Ooh.
Chandra.
All right. That's good. Hi, everyone. Welcome to Astronomy on Tap.
Welcome.
Are you guys excited for tonight? Yeah. Woo-hoo. I hate doing this, but come on, guys. Are you guys excited for tonight? There you go. So my name is Tracy Becker.
My name is Vincent Hugh.
And we will be your hosts tonight. We run Astronomy on Tap pretty much monthly, but we could not do this, and especially this event, without some of the amazing team that we have running Astronomy on Tap. So just a quick shout out, and if you're in the room, go ahead and stand up, but a lot of them are outside still working right now. Adam
is here.
Sam, Lizette, Christine, Brian, Elisa, Ben, he's the 6'9" guy that you might have seen pointing you in this direction, and Ethan has been at checkout. So we really can't do this stuff without them. So we're really, really, really grateful.
All right. So let me first ask you, what is Astronomy on Tap? How many of you have been to an Astronomy on Tap presentation before?
All right.
The San Antonio one? So how many of you have been to another location other than the San Antonio one? Oh, just one here, one here.
Rudy.
All right, so Astronomy on Tap is an event that is designed to bring science to the public in a fun and entertaining environment. It was initially created in 2013 by Dr. Meg Schwan in the New York area and became extremely popular. So this map, for instance, shows the distribution of all the Astronomy on Tap in the world, mostly in the US, but also a bit in Europe, in South America. And 2 years ago, we decided to bring this event in San Antonio. And so far, so good. We became quite successful because this is our 19th event. So thank you guys for your support. And we're also very proud to be part of this organization, this worldwide organization that has created, since its creation, 2013, over 1,000 events like this one tonight over the world. So it's pretty incredible. And this event, the 20 years anniversary of the Chandra spacecraft launch, the Chandra Observatory launch, has been celebrated by Astronomy on Tap over the world this year. So I'm going to let Tracy now to talk to you about our sponsors.
Yep, and so again, I already talked about some of the volunteers that make this happen. We are extremely grateful for the businesses and local businesses that have also made this event possible. The Southwest Research Institute, we'll hear a little bit about them. Yeah, all right, I like it. The American Geophysical Union actually gave us a grant to help support and fund this bigger event that we're having here tonight. And UTSA Astronomy and Physics Department also helped us out, so thank you. Go Roadrunners. And of course, our sponsors and our extremely generous donations from Beer Blue Star Brewing Company. If you guys don't know, that's where our events are usually held, so we're super grateful to them for bringing some more beers out here tonight. We've got Boulevard Beer, we've got Blue Moon, Dorsal, Kunstler, and Freetail, also all beer outside. So if you guys haven't tried some beer during the break, make sure you go out there and get some. And with that, so we are, again, like I said, very grateful to Southwest Research Institute. Not only are they supporting this event, they also support us as scientists there, and are generally a big source of our speakers in overall. So we're really excited to welcome the president of the Southwest Research Institute, Adam Hamilton.
Tracy thought I wanted the microphone. No, that's not the case. What a great event. Thank you very much to the organizers. Can you have a better event than something fueled by astronomy, science, and beer? I'm there. So, Southwest Research Institute, you probably have heard of before. Most of you are from San Antonio. What do you think of when you hear Southwest Research Institute? Monkeys! Well, I have some bad news for you. That's not us. Okay, I'm going to push a button, see what happens. That's not it. There we go. So we have a little bit of an identity crisis, even though in this crowd, I'm sure we're pretty well known. So we're always trying to figure out, what do we say when people ask, well, what does Southwest Research Institute do? Well, that picture on the left, that is the pressure hull for the Alvin submarine. We did the original pressure hull back in the 1960s. In 2014, we redesigned that pressure hull, fabricated it, and tested it. So now, the Alvin submarine can now dive to the deepest depths of our oceans, over 99% of the ocean floor. And then I'm sure this group probably recognizes that image. Don't tell me that's the moon, okay? You all have to get this right. What is that? Pluto. Yes! I do this, and many audiences look at me and they think, Earth. I think I'm wasting my time when that happens. That's Pluto. And now, also then, following Pluto, that which was humankind's furthest exploration, we doubled down on that and flew by this object, and this group probably knows the name. Ultima Thule, right. It just so happens, if you abbreviate Ultima Thule, you get UT. I had nothing to do with that. So when we developed the first false color images, they were burnt orange. I just don't know how these things happen. It's amazing. So instead of thinking of the monkeys when you hear about Southwest Research Institute, think about this, deep sea to deep space. So I realize Ultima Thule is not really deep space, but because of the astronomers, who is an astronomer from Southwest Research Institute here tonight? Thank you. Kurt? That's all? Okay, there you go. So we truly do deep space as well as deep sea. So on behalf of Southwest Research Institute, I'd like to thank Tracy and the entire team that helps put this event on, Amanda Bayless, who is not here tonight, but they do a fantastic job with Astronomy on Tap. So if we could give a hand to Tracy and everybody else from Southwest that's here. And I have to put a plug in for San Antonio because I'm also the chair of the Chamber of Commerce right now. So glad you're in San Antonio. Do business here. And I think Tracy or Vincent's going to introduce our speaker, but Dr. Eileen Collins is one of the most remarkable people that I think you'll meet. All of the accomplishments, all of the science that she has done, all of the expertise, all the things that she's done to advance the fields that we're very interested in have benefited from her contributions. But you'll find it very difficult, if not impossible, to meet somebody who is more humble than she is. So we're honored to have her as an advisory trustee and look forward to your comments tonight. Eileen, thank you.
All right. So tonight I'm very excited because we have a special guest that directly flew from Boston for this event. So let me introduce to you Dr. Rodolfo Montez, who studies the evolution of stars, and especially the ones that are dying, the ones that are transforming into a nebula. He is an X-ray expert, studying both the diffuse and compact emission on these celestial bodies. But he's actually from San Antonio. Yeah. He went to San Antonio College right after high school, graduated with a Bachelor in Science from UT Austin, and then got his PhD in Astrophysics from the Rochester Institute of Technology. And now he currently works at the prestigious Harvard-Smithsonian Center for Astrophysics that is located in Boston. And tonight, as part of the science team that operates the Chandra X-Ray Observatory, he will give a talk on, which is titled 20 Years of Science with the Chandra Observatory. So make some noise for Dr. Montez. So it's down to...
I'll do this one. Okay. All right, can you all hear me back there? Good. I'm going to try to stand back here so I don't create a lot of feedback. I'd like to thank the organizers, first of all, for having me here and for bringing me all the way down back to my hometown, which is always a pleasure to visit. Like I said, I'm going to talk about 20 years of Chandra. Chandra is a satellite that's in space that was launched in 1999, and it's been doing X-ray astronomy for 20 years. And believe it or not, but I have 70-something slides to do in 15 minutes. All right, so without further ado, I'm just going to get started, and I'm going to tell you a story from 1574, which I wasn't around then. I don't know if anyone in the room was around then. But back then, we didn't have the cameras that we have today, so we actually had to draw our observations with pencil and paper, and that's what you're seeing here is a drawing from a Danish astronomer, Tycho Brahe. And the thing that he's noting in this image is this star labeled I. And it says Nova Stella, which means new star. It was a star that appeared in the night sky, and it was so bright that it was actually visible during the day. And it was visible for the day for about a couple of weeks and months, and then it faded below detectability by the human eye. So fast forward to today. This is this image of the same part of the sky, centered right there in the middle, is the bright star that Tycho Brahe noted back in 1574. It doesn't look like much, right? And that's because this is a camera that's using light, like the light that we can see with our eyes. And so it's studying that light, and it's making an image in what we call visible light. And it doesn't look very exciting. But when you turn an X-ray telescope to that piece of sky, this is what you see. This is the remnants of what was there at that point, where that bright star that he saw back in 1574, this is the explosion of that star hundreds of years later. And we see it only in the X-rays because it's very hot. It's about 10 million degrees Kelvin. Kelvin is a temperature scale that we use, but when you're talking about millions of degrees, it doesn't matter if it's Celsius or Fahrenheit, it's hot, right? Everything is 1 million degrees at that temperature. And so this is a 1 million degree gas, and you only see it in the X-rays, and this is why we put satellites into space. We have to put them into space because those X-rays don't actually penetrate our atmosphere. They're absorbed by our atmosphere, blocked by our atmosphere, and so we can't see them. So we have to put them into orbit above the Earth in order to see the X-rays. This is an image taken by Chandra. The previous one also was taken by Chandra. And this is just after launch in 2000. I'm going to show you a picture now from about 15 years later. Yeah. So if you look, you can actually watch that supernova remnant, this is called, you can actually watch it expand over those 15-year time frame. It's quite spectacular. And all of that started from this little tiny drawing back in, I was saying 1574, but back in 1572. And that's all that sky right now. This is why we put these satellites into space, in order to study that energetic phenomenon. So right about now is where I'd go into this long story about the spacecraft, but since we have Eileen here, I'm not going to spend that much time on this section of my talk, just to tell you that this is the spacecraft with people around it, to give you a sense of the scale. That's this part of the spacecraft here. There's a long empty tube, and then there's cameras at the end. These are the mirrors of that spacecraft. And this is really the powerhouse of Chandra, the thing that gives it its superior resolution to look at space with X-rays. X-rays are very easy for us to understand because we use them all the time in medical imaging in order to look at broken bones. And what is actually happening there is the X-rays are penetrating your skin and they're being blocked by your bones. So you're actually looking at an X-ray shadow in an image like this. And that same concept is why we can't make X-ray mirrors in a very traditional sense. We can't just have a mirror that reflects light because it'll be absorbed. The X-rays will be absorbed by that kind of mirror. So instead, what we do is called a parabolic shape kind of mirror. There's a technical name for this, which essentially, if you imagine a mirror like a parabolic shape, like that, and you chop off the bottom, and you're left with essentially a cylinder. And that cylinder is what focuses the light into a focus. And I'll play this video, hopefully. Yes. Showing you here, a normal mirror would just absorb those photons and you would not see them. So what we do is chop off that end, and we deflect the photons in the mirror all the way back to the detector. It's a lot like if you're skipping rocks in a pond. You can't throw the rocks down. You have to throw them at an angle, low to the ground, and then that will cause them to skip. We're doing the same thing with the photons, or the light that we're detecting, the X-ray light in this case. This is the orbit of Chandra, but maybe we'll talk about that later. Just to remind you that we launched in July 23rd, 1999. I like this slide because I like to go birding just down the street here on Avenue A back when I lived here, and I really like these birds, which you can see there. I really like to imagine what those birds must have felt like when that rocket took off. They are probably terrified and leaving all kinds of droppings down there. But we'll talk more about that later. Let's talk more about the science. So this is one of the first images that Chandra took. It's of another supernova remnant called Cassiopeia A. And right off the bat, that bright spot in the middle, this is all beautiful and everything, but that spot was the first time that we saw the remnants of a star that has died. That's the neutron star left behind from this explosion of this massive star. Of course, we look at objects again, we get better signal, and in this case, we have more pretty pictures to show you. This is actually light coming from different elements in that plasma, and I'm showing you the breakdown up here. This is just to tell you that these color images are really beautiful, but they're also scientifically relevant, and they help us understand the processes that are happening in these supernova remnants. So now we're going to do a little tour of the universe in the remaining time that I have. This is the Jupiter. This is coming from the Hubble Space Telescope. I'm going to show you now what we see when we point Chandra at Jupiter. Okay, maybe it's not too exciting to you, but it's very exciting to a lot of people at Southwest Research Institute. who actually propose a lot for these observations. So we're actually studying X-ray emission coming from the polar regions of Jupiter. And it's coming from a process a lot like what we see here on Earth in the aurora. Here on the Earth, we see these beautiful aurora that are caused by our magnetic fields and charged particles interacting with those magnetic fields. The same process in this artist's illustration is happening around Jupiter. And when we look at those X-ray emission, we can study those processes in better detail. This is the Earth, not Jupiter. But maybe someday we'll have a probe on Jupiter that'll look at something like this in the X-rays. So this is an image of the sun. This is not taken by Chandra. This is taken by a series of satellites that are always looking at the sun in X-rays in order to study the energetic flares coming from it. I have this image up just to tell you that we cannot look at the sun because it's way too bright and it'll fry all of our instrumentation. But stars, like our sun, emit X-rays through what's called a corona. And if you had the good fortune of seeing this total solar eclipse back in August a couple of years ago, you could have seen that corona with your naked eye for that moment of totality. In this corona, you can see all of these streams of material. All of this material out here is about a million degrees in temperature, and it emits primarily in X-rays. So we can look at other stars that are farther away. We can't look at our nearest star, but we can look at other ones. And this is the Orion Nebula here, the Orion cluster here. I'm sorry, constellation. Those are the belt stars of Orion, and that's the sword of Orion. And that middle star right there is actually a stellar nursery where a lot of stars are being born as we speak. This is what it looks like with the Hubble Space Telescope. Again, beautiful, lots of gas and dust in there. All of those points of lights are newly forming stars in this stellar nursery, and all of that gas and dust is what those stars are being formed from. If we take a look at this tiny region in the middle, and we blow that up, it looks pretty dusty, pretty gassy. You see a few points, but when we point the X-ray telescope there for about 18 days, this is what you see. I'll go back. So all of these points of lights are coming from stars that are recently born, and when they're recently born, they're active, and so they're creating a lot of this coronal emission, and that's what we're seeing in the X-rays. We're seeing accretion from the disk as well, and those disks around those stars are going to form planets, and so this whole region of space is just filled with a lot of processes that are helping us understand the formation of planets in our own galaxy. These star-forming regions exist around other galaxies as well. So this is M51, the Whirlpool Galaxy, named for this shape, not the washer and dryer. And you can see all of these red spots that you see along here, and this gas and dust. Those are star-forming regions just like that one that we saw in the previous image. But these are at a much greater distance. And so those are sites of active star formation that are happening today. If we look in the X-rays, this is what we see. I'll go back again. Pay attention to this dark lane here and watch it in the next image. You can see the dark lane is still there, and that's because there's so much dust, and we have to look through that dust, but we can't always look through it because it absorbs our X-rays. Here's a composite of the two. The purple hue is showing you where the X-rays are coming from. That's just one galaxy that's nearby. This is our galaxy center, also called Sag-A star. It's the center of our own galaxy, and we know there's a supermassive black hole in there because if you look long enough with a really high-resolution optical telescope, you can actually track the motions of those stars, and they seem to be orbiting around an invisible thing. And as these stars approach it, they sling around, and from that sling, we can actually tell how massive that object is, and we know that it's something several million times the mass of our own sun. And it's not visible, and so we think it's a black hole, what we call a supermassive black hole. Supermassive black holes are very energetic sites in other galaxies. In our own galaxies, there's a lot of X-ray emission coming from all of this energy that's in the center. If you ever want to stare into the galactic center, which I like to do sometimes, You can find the teapot, and if you can find Scorpius, just look there in the middle and you'll be staring straight into that black hole. No harm will be done to your eyes. So there are other black holes in other galaxies. We now think they're ubiquitous in most galaxies. This is the galaxy called M87. This is a Hubble Space Telescope image. This is Chandra. Same scale, just showing you how different the types of emission can be. And there's that supermassive black hole in the center. If we zoom in there, you can see there's a jet of material that's being shot out at very high velocities. And if you remember, this is the very same galaxy where we imaged the black hole in the center using the Event Horizon Telescope, which is also operated out of the CFA in Boston. This is another active galaxy with one of these jets that I pointed out. In red, you're looking at radio emission, which is coming from a different type of light, different wavelengths of light. And in blue, you're seeing the X-rays. Here's just the X-rays showing you this pencil-thin beam of emission ending in a hot spot out there, all coming from that supermassive black hole in the center. And here's just the radio emission, and again, the composite. We see that every time we look at these massive galaxies. If they're close enough to us, we can actually resolve that. If they're too far, we can't resolve it. Here's a bunch of galaxies. Each of these are different galaxies, believe it or not. It's called a galaxy cluster. This one is called Stephan's Quintet because there are 5. I'll show you the 5 in a moment. This is what the X-rays look like coming from that region. And if I go back, each of these circles is showing you the center of those galaxies. And if I show you now that same image in X-rays, you can see that we have bright spots in each of those coming from that active core where those massive black holes are. And then you have this sausage-shaped structure in the middle. That sausage-shaped structure looks pretty innocuous, but it's actually quite interesting. Oops, there we go. It's coming from the interaction of these galaxies. These galaxies are, hundreds of thousands of stars gravitationally bound to one galaxy, and then these other galaxies are now gravitationally bound to themselves as well. And so you have all of these stars and all of this material gravitationally bound and interacting on timescales that we can't even begin to comprehend. And in those processes, they create shocks or high temperature gas, and that's what we see in the X-rays. Here's another galaxy cluster, believe it or not. Everything in this image except that, and that is a galaxy. Everything in this image is a galaxy except those 3 or 4 stars. And this is what it looks like in the X-rays. I don't believe it, so I'm just going to blink back and forth. But there's a composite of these 2 images. All of this swirly material that you see out here is from this interaction happening with these galaxies as they swirl around each other. It's really quite phenomenal, and it's thanks to the high resolution of Chandra that we can actually do this type of study. So the next thing I'm going to show you is one more galaxy cluster. This is actually 2 galaxy clusters. I know it's hard to see them because, again, everything in this image is a galaxy except for that. Everything else is pretty much a galaxy. So lots of galaxies. There's actually 2 galaxy clusters here. There's one galaxy cluster here, and there's another galaxy cluster here. And if we look at that in the X-rays, this is what we see. This is the X-ray emitting gas. So all of the pink that you see here, this is hot gas from these 2 galaxies as they interacted with each other. And what we actually think is happening is this galaxy has flown through this other cluster. This galaxy cluster has flown through this cluster and has left this wake behind it. Much like you might expect a boat to leave when it's a boat to leave as it goes through water, it leaves this wake behind it. This galaxy cluster has done that also. Another thing I want to point out about this is all of the emission that you see in pink is coming from gas. And that gas is normal gas, like matter made of you and I, but it's just very hot. If you sum up this mass, it weighs more than the mass that you see in light. The mass that's coming, the mass that's due to the stars that are emitting in the optical. And so most of the ordinary matter in these clusters is coming from the pink emission. And so you need to study X-rays in order to trace that matter. But there's another matter that's present, and it's called dark matter. And we know this from this observation in particular. What I'm showing you here in blue is essentially the mass map of these objects, these two galaxy clusters. So this cluster has a very large concentration of mass here, and this one has a large concentration of mass here. And we do this through a technique called microlensing, which allows us to map out the matter distribution of all matter, dark and ordinary matter, in these galaxies. And we find that these two galaxies have these massive dark matter halos. And the way that we know that is because the ordinary baryonic matter is again in pink, and it's lagging behind the matter that you see in blue there. And so that separation is actually a prediction of the interaction of this dark matter as it passes through the other dark matter from the other cluster. So we've done all of this beautiful stuff thanks to the Chandra X-Ray Observatory. And believe it or not, this is slide 76. This is the Chandra X-Ray Observatory, which I've told you about, and I think I'm good on time. 1 minute, perfect. So I want to leave this slide up and tell you that we have some really cool things that you can see online. If you go to our website here at thechandra.si.edu, you can actually take a tour of the supernova remnant. We made a 3D model of it, and it allows you to look on your phone and move around it and go through it. We also have a simulation of the center of our galaxy, which you can also do in VR. If you have a YouTube camera, you can do it with goggles, or you can do it just with your hand, and it'll let you see the center of our galaxy, the Milky Way galaxy. So thanks a lot for your time. I'm happy to take some questions.
I'll give you this microphone and go through the room with this microphone. Yeah. So, and yours. Okay, so guys, we have 5 minutes for questions. So if you have any questions, raise your hand, and I'm going to go with the microphone as fast as I can. You had a question? No? Okay. Oh, there's some questions here.
First, thank you. That was a very nice talk. My question is about the Orion Nebula, and it looked kind of like there was a lens flare of some sort in that image. I was wondering if that was real and what was causing it.
Are you talking about the X-ray image or the HST image?
Oh, I don't know.
This one?
No, forward.
That one there?
No, forward.
This one?
Yeah.
I have a question over here.
That it's actually coming towards us. So I was curious about, you were saying it's actually, firing left, but surely it's actually firing this way.
Yeah, so this is actually, there should be a counter jet on the other side. This one is headed in our direction, and so it actually gets a boost from a relativistic process, and that allows us to see it even brighter. The other one would be seen if we were on the other side of it. We could see the other opposite jet.
So we have a question here.
So you're saying it's going from left to right, but what if it's going from right to left?
Not in this case, but in other cases, we can actually measure the proper motion of those jets, and so we can actually see them evolve and grow in that direction. If I said left or right, I may have got it backwards because I'm left-handed, but I mean, it's going that way.
One more question, same image. You indicated that it was ending at that right side point. What do you know about that right side? Can you expand on that a little bit?
Yeah, this bright spot here?
Yes.
So you see this red material here. This image doesn't look as great on my screen, and I recommend going to our website where you can see all these images in a little bit higher fidelity. There's a lot of material here, and so that jet is actually interacting Whether or not it's punched through and it's still out there, but we just can't see it because it's too faint, that's an open question. But as it passes through that material, it creates a bunch of shock gas, and that's what we see there in the X-rays.
Do we have any more questions here? Okay.
Hi. Okay, so you mentioned a star at the beginning that the Dutch astronomer was studying. Do you know when did that one explode or implode? When was that?
So we based on, so the rise time of a supernova explosion is very quick, and so 1572 is about when it happened. However, you have to account for the fact that it had to travel some distance before it got to us. And I'm not sure how many light years it is away, unfortunately. I wish I did have that on the top of my head, but we do know, I just don't know.
Okay, so we have time for one. There was a question around here. Yeah.
Hi. What motivated you to name it specifically after Chandra?
That's a really good question. And actually, this was actually a contest that we had, believe it or not, a naming contest. But it's mostly coming from the Indian astronomer Chandra X-Ray, who discovered a fundamental limit on the size of one of these dead white dwarf stars that they can have before they supernova, before they explode. And that's where the name comes from. And that was actually done through a contest where people actually mailed in a bunch of requests and explanations, students and the like, and then they were selected from that.
Thank you.
Right, I think we're done with questions.
Yeah.
We're going to take a 10-minute break, so 10 minutes break. So please grab some food, grab some drinks, and make some noise for Dr. Rodolfo Montez. That was awesome.
Yeah,
Good job.
15 minutes.
the lapel, and then
So it would be better if she had the microphone, so
Yeah,
we don't have to
the
switch
lapel.
doors.
yeah.
But I know I think she preferred that.
Okay, I'll ask her.
And the microphone is right here.
Check, check.
All right, guys, we're gonna start in a minute. Check, check, 1, 2. 1, 2, 1, 2.
Check, check, check. Okay, I'm sorry, we're gonna have to get started, but. Oh, sure, go for it. Oh, great.
So I just want to say thank you very much. You took my baby into space. I worked on Chandra all the way up to STS-93. And I wasn't working. All I wanted to say is thank you for getting her up there safely. Yeah.
Awesome. Team effort.
Can I get a quick picture? Maybe out your way. Do you mind? Doesn't matter.
Check, check.
Up there, you have a tendency to turn your back on everyone or like too much side. Try to stand here.
Okay, so we're gonna get you mic'd up. Do you need a?
I put it on the second.
Okay, I don't have to switch anything there?
That should be okay.
Okay.
And also, so you said STS-93 was your third mission.
Yes.
And that was also the launch of the third out of the 4 great observatories?
Yes.
Okay.
Very good.
Just wanted to make sure I said that.
Okay.
Sam
Yeah, I'll talk for
Toback,
about
please
2
report
minutes
to the
and then I'll
front.
say,
Sam
let's roll the
Toback.
video.
Oh, I see.
I'll do that. That's the code name.
I say, let's roll the video. How's that? I've been talking so much, I now have a frog in my throat.
Yeah.
Now, who's going to turn this on? I don't have to throw a switch, but somebody over here is going to turn it on. I don't have to throw a switch.
Hey, Vincent.
Floater walker, you're going to be walking around or standing up by the podium the most time?
Both.
Okay.
I'll walk around these.
It seems to get more feedback if you come in front of this because those speakers, like, there's some that go down, I think, and some go out. So the more you come out here, I think it has more feedback.
So if I stay on the stage,
good.
I'll stay on the stage.
A couple steps just,
And maybe test.
you'll try to make sure it stays below zero, but I don't think so. No. You'll hear it. Well, I say that. You get up here loud right now? You look at the the bottom of that.
I'll just say. Okay.
Green lights on.
Okay. Okay. Guys, we're gonna get started. No one can hear me. It's working, it's just so loud. Okay, guys, we're gonna get started. I can do that better. Check. Y'all can hear me? All right, great. So welcome back for the second half of Astronomy on Tap. Just before we get started with the next talk, I did want to mention that we do this every month. And so next month, we will be back at our normal spot at the Blue Star Brewing Company. It's going to be on our normal day, which is Wednesday, November 13th. So come on out for that. I also really quick want to promote the fact that there are other ways that you guys can get drunk and learn about science. There's another great group around town called Taste of Science. So you can go to their site. They've got an event going on at Friendly Spot on October 30th. So if you can't wait until November 13th, don't worry. You only need 2 weeks to wait for the next time to drink and learn about science. So it's great.
Go on the stage. Go on the stage.
I can go on this. That way people can actually see me too. Okay. So it is with my great honor, privilege, excitement that I introduce Colonel Eileen Collins. She is a retired Air Force colonel and astronaut. Yeah? It's pretty good. She was the first female pilot and also the first female commander of the space shuttle. The mission that she's going to talk about today, since we're on the Chandra theme, the mission that she's going to talk about is the STS-93. That was the third of her 4 shuttle missions, and that also happened to be the mission that launched the third of the 4 great observatories. So that's a nice anecdote. Colonel Collins also logged 38 days in space. Is that true? About, approximately? She lost count. She lost count after like 25. And she's also, among many other accomplishments, she is currently serving on the board of advisors for the Southwest Research Institute. And so again, we are really, really grateful to have her out here. She does, among many other things. It's amazing that she does do as much for the community, to talk to students, talk to people in the community, and tell us a little bit about her experience as an astronaut. So we're really grateful and really honored for you to be here tonight, and we're really excited to hear your talk. So with no further ado, Colonel Collins.
Okay, thank you. I hope everyone can hear me. If you can't, just let me know and I'll speak up. First of all, thank you all for coming out. It's great to see all these people that are interested in astronomy and interested in our space program, which is absolutely wonderful. Want to give you a little bit of background. I'm going to narrate my crew movie tonight, but before I do that, I want to give you a little bit of background on how the mission came about for the crew. So we all know that Chandra has been in conception and innovation since back in the 1970s. But my crew wasn't assigned until March of 1998. So I've always been an astronomy geek, I would say, especially the years I lived in Oklahoma. I loved going out in my backyard and looking at the night sky. And I loved astronomy so much, I joined the astronomy book club and I subscribed to Astronomy magazine. I bought 2 telescopes and that was my hobby. And I always thought, you know, well, maybe I would like to go out there and see what it's like. Well, I became an astronaut and we were flying the Hubble missions, we were flying the Hubble repair missions, there was a gamma ray observatory mission. And by the way, Hubble and the gamma ray and the Chandra and the Spitzer are the 4 great observatories. And I was talking to my boss one day in the hallway and I said, you know what sure would be great to fly one of the astronomy missions? And just made a comment. And what do you know? I got assigned to the STS-93, which at the time was called the AXAF, AXAF, the Advanced X-Ray Astrophysics Facility. Maybe this will work. So I try to figure this out. So, and my crew got assigned in March of 1998, and I remember telling my crew, we have a great responsibility. $2 billion is what it cost to make this back in those days, and there's only one of them, so we are not going to mess up this mission. We are going to be the absolute best we can be. There were 5 crew members. I'm going to introduce them to you as we go through the video. They were a great team. I just love these guys and gals. We had a training team, we had a mission control team, we had engineers, we had the people that built the Chandra in the factories that was built in Southern California. Which is now Northrop Grumman, but back then it was TRW that made it. We would go out there and meet the people and talk to them, and we'd learn as much as we can about AXAF, which eventually became known as Chandra. And my crew also needed to know the telescope very well as the booster that was attached to it. And you'll see in the video, there's a booster called an IUS, Inertial Upper Stage, that was attached to the back of Chandra, and that was deployed out of the shuttle payload bay. Now, a lot of people don't know, but the space shuttle only had so much gas, it can only go to low Earth orbit, which is maybe 300 miles at the highest. When we deployed Chandra, we actually went to a little bit of a lower orbit, about 150 miles, which is relatively low for a space shuttle orbit. But because the Chandra had the IUS, Inertial Upper Stage, which is a solid rocket booster, once we deployed the Chandra, checked it out, the controllers in the IUS Control Center lit that rocket and sent it up to Chandra's final orbit, which was highly elliptical, and it goes about 1/3 of the way to the moon. And we in the shuttle stayed down in low Earth orbit. And one of the benefits of getting Chandra out there is to get it farther away from the Earth so it can get an even clearer view, outside of the Van Allen belts, and give it a place where it can get even a clearer view without the background of the Earth interrupting it. So I think that's enough of background. Let's go ahead and roll the video. And I'm going to narrate through this, beginning with some of the training scenes. So my crew was in training for about a year, about 15 months, preparing for the mission. So you're going to see many different things that we did, beginning with we each got our assignments. We designed the patch, we got a crew photo done, we did all that administrative things. And then we started specifically doing a training syllabus, which began with emergency crew training. So this is some of the training that we did. If we had to bail out of the shuttle, which we could do, if for some reason there was a problem on launch, we didn't want to do this because we had a $2 billion telescope in the payload bay, but in the event that we lost our engines or had some kind of a problem with our payload and had to come back, we had to know all of the emergency procedures. Who you see here, wanted to introduce my crew a little bit. This is Steve Hawley. Steve Hawley has a PhD in astrophysics. He was on the Hubble deploy mission, so we flew him again on the Chandra deploy mission. Michel Tonini is a French test pilot as part of the international program. He was on the Chandra deploy along with Katie Coleman, which is next to him. This is the Chandra in the payload bay of the shuttle. This was taken about 3 days before launch. We suited up and we went out there to the launch pad. The payload bay doors were open. There's kind of a room around you to keep out the rain and the mosquitoes. And we got a chance to take one last look at Chandra. These are some of the simulators that we did. You just saw the fixed base simulator where we would train various deploy scenarios inside of the Columbia space shuttle. So we actually launched with Columbia. We also had EVA training, which is extravehicular activity or spacewalking. and to do that, so we're in a pool. This pool is 25 feet deep. It's called the NBL, the Neutral Buoyancy Lab. We had the space shuttle payload bay along with the IUS and the Chandra mock-ups under the water so they could actually be neutrally buoyant. And Katie and Michelle trained for various problems that might happen in case they had to go out and do a spacewalk to fix it. Also, not many people know, but we had a Southwest Research Institute payload on this flight called SWISS. And here we're training with SWISS. It was a ultraviolet telescope that we put in the side hatch right here to do observations. After the Chandra was deployed, we did observations in the ultraviolet. This is some classroom training we did, Earth observation. We'll talk more about that later. But in some of the extra time we have, we also we don't just look out to the deep space, but we also look back at the Earth. These are T-38 jets. This is Katie Coleman. Katie was primary on the deploy of Chandra. And Steve Hawley. So the astronauts trained, and we still do train in the T-38 aircraft to give us the spaceflight readiness training, getting us into an actual environment where you're wearing a G-suit, you're wearing a parachute, you've got a helmet on, you're talking on the radio. We're doing formation takeoffs, we do acrobatics, we do instrument flying, and all of that is real-world training that we do that prepares us for spaceflight. You can load up the Gs on the airplane, you can pull up to 7 Gs in the T-38, although in the space shuttle we only go up to 3 Gs. We train the T-38. Okay, now we are down at the launch. So we were in quarantine for about 10 days, so the crew is medically isolated from the rest of the world, so we don't get sick. We want to be ready to go on launch day. Our launch actually happened around 12:30 after midnight on July 23rd, and we strap in about 3 hours before launch. And we're doing the launch countdown. You know, once you get the crew strapped in, you close the hatch. We're watching the countdown clock come down, you know, through T-minus 31 seconds. The onboard computers take control, and when that happens, you know, yeah, we're probably going to launch today. And then T-minus 10, 9, 8, T-minus 7, T-minus 6. It's 6 seconds the engine's light. And it takes 6 seconds for them to fully come up to speed, and then at T-minus 0, the booster's light, and you're off the launch pad. And I'm going to tell you, there's a lot of shaking going on. But the Chandra's doing okay. You know, you worry about that very sensitive telescope, but it is built to survive the stresses of launch. So a lot of shaking going on. I mean, if you tried to write on your knee pad during the launch, you'd never be able to read it because your hand's moving all over the place. Inside, it looks like you're in a room that's on fire. It sounds like there's a fire burning around you. You see a lot of flashing, looks like a thunderstorm. And also, we accelerate up to 3 Gs. And you feel that G accelerate. You know, what is a G? Here on Earth, you experience 1 G. So let's say I weigh 100 pounds on Earth. If I could stand on a weight scale during the launch, it would register 300 pounds. And that's how much force is being put on you during the launch. But the Chandra and all the associated equipment is built to withstand those forces. So after 8.5 minutes, we made it up to space, opened the payload bay doors, and we got a beautiful view of the Chandra. And you know, it survived. We had people on the ground up in Boston at the Chandra X-Ray Center, and the Air Force people out in California, out in Mountain View, were watching the IUS, and they reported to us that the data looked good, and we were go for deploy. So about 7 hours into the flight, on flight day 1, we kicked Chandra out of the payload bay. But to do that, there's a long procedures, a lot of checklist steps that we have to go through. The crew's doing, well, you see Katie there with the camera on the right. All right, so this view is looking out, if you can imagine the shuttle cockpit, you're looking out the back window toward the payload bay. And this is, we activate the tilt table. So at the very back of the telescope, we tilted the entire assembly up to 45 degrees. Actually, we stopped around 20 or so degrees, ran a bunch of checks, passed, and then we tilted it all the way up to about 45 degrees. And that angle, if you can imagine, if my arm here is the shuttle, we tilted the Chandra up like this and deployed it straight out over the top of our windows. So again, we ran communication checks, navigation checks, electrical checks. At the very end here, this is the, go back to that view. What you were just looking at is the imaging instruments at the very end of the telescope. And at the moment of deploy, This is the IUS. And this view is from the back of the shuttle looking forward. You can see our windows here. The crew is up in the front. This is the rocket engine that's going to fire in about an hour or so. There's the IUS. And the Chandra's up here at the top. So we deployed it with a spring. It went very, very, very slowly over the top. Okay, here's the cruise view looking out the back. My laser pointer's not working, so I'm going to get one that works. Okay. And this is the view out the overhead windows of the back of the IUS. And here's the Chandra on the outside, and you're kind of looking straight in. I mean, imagine that going like, here we go, this is a better view. This is a view from the back of the shuttle payload bay. Here's the Chandra mirrors, the imaging instruments on the end. And just a view with the crew. So we all grabbed cameras, so everybody's taking pictures of, we had high definition cameras, we had old cameras, we had still, we had video. And again, here's Chandra right here, here's the imaging side, here's the booster, there's the rocket. And there's sunset. So we said goodbye. We were the last people to see Chandra. It went off, and then we started doing our other activities. In about an hour, we wanted to know, did that rocket light? Yes, it did, and it was successful. There was a full burn, and Chandra made it to its final orbit. So now we got busy doing our secondary experiments. This is the Swiss experiment I talked about earlier, which is the Southwest Research Institute imaging Jupiter, and there's the Jupiter moons. And that imaging is in the ultraviolet. This was an image of the moon in ultraviolet. The one you saw at the beginning there was Venus. And the principal investigator on this was Alan Stern, who also worked the New Horizons mission. So we spent quite a bit of time with him. So Katie had an experiment where she was growing plants in space. So these plants had a specific gene sequence in them that was where the researchers were able to tell how stressed out these plants were based on being in microgravity compared to their control back on Earth. So this is kind of a fun thing for astronauts to do, to watch plants grow. And then you can spin them around to get the video of it. So some of the other secondary experiments we had were growing spores. So these dishes on the wall was Jeff's experiment, and it was spore growth. And again, they have a control experiment on the ground, and we videotape and we log the data up in space, and we got some, not the best view, but you can see how. Okay, this is a caterpillar experiment. So this is, take a look at this guy. They actually turned into butterflies during the mission. This is a solar array hinge experiment. And we were looking at new technologies for future solar array deploys off of satellites. We do a series of burns to raise and lower our orbit, and there was the OMS engines. Burned is just a little bit of a puff, and you get a second of gravity. Our treadmill, we were testing a treadmill for the space station. So you use these bungee cords around your waist and around your shoulders. And it's great to have the exercise in space. Not just because we know it's good for you, but it makes you feel better to get a little bit of gravity after floating in microgravity for so long. Okay, so Michel over here was our French cook. So he made some really great food for us, and he was able to cook some actually before the mission. And they freeze dry it and send it up. And Michelle's also showing the vacuum cleaner, so the guys and the gals all take turns vacuuming the filters. This is a LiO canister, lithium hydroxide, which we use in our environmental system to take the carbon dioxide out of the air. Okay, Steve is on the laptop. So we did a lot of experiments for the kiddos. So some of these were physics in space. So Michelle and Katie had they put a video together for the kiddos. You can't really make bubbles in space very well, but you can make, this is actually a blob of water. So we had a contest on the crew, who could make the biggest blob of water before the thing blew up into a lot of tiny little pieces. Here's some views of Earth. So we lowered our orbit down a little bit, so we're actually quite low here, only about 100 miles above, because we're doing some observations. This is the Great Barrier Reef, which is just to the east of Australia. And a group of scientists are studying these are the Society Islands, but we know that by studying the Earth's, we call this Pork Chop Island, by the way, but by studying the Earth's solar reefs, we can learn more about the oceans. So we got data for the scientists from space. Night view of, you know, when you look out the window at night, you're going to see thunderstorms going off somewhere. And just another beautiful view of the Earth. Empty tilt table, which meant we had a successful deploy at Chandra, and we're getting ready to come home. So we put away all of our secondary experiments. The crew was very happy because we knew that we had accomplished our mission, but we still have to come home. So this is us right here, leaving a streak over Texas. Some of you might remember in, I think it was July 29th or something, on the 10 o'clock news, the newscasters were saying, hey, if you want to see the space shuttle fly over, go outside at 10:06. And people saw us fly over Texas from San Antonio, Dallas, Houston, Austin, and people still talk about this. We're cruising across the sky there at 200,000 feet and Mach 10, 18,500 miles an hour. This is a view from Kennedy Space Center. We came into land. This is an infrared camera which shows the heat signature of the shuttle. You know, we heat up to almost 3,000 degrees while we're up there. And slowly cool down as we come down final approach. This is the view out the window. It's a heads-up display. Altitude over here, airspeed over here. I'm flying this guidance diamond in the middle, making a right turn. I'm going to land on runway 33 at Kennedy Space Center, and it's probably about 10:30 at night. We come down final on a 20-degree glide slope. It's about 7 times steeper than a commercial airliner. And I'm looking at, these are called PAPI lights, precision approach indicators, and I'm following, there's my altitude, my airspeed, I'm following this guidance diamond as I pull up. Here's the runway. We've got xenon lights, there's the approach end. I want to land right here where the centerline lights begin. And I want to land at that spot at 195 knots, which is close to miles an hour, and I want to be right on the center line because all the shuttle commanders compete with each other on who can make the best landing. And here's the ball bar, which brings me in over, you want to be 50 feet over the threshold. And we had a nice smooth night, just a very, very light crosswind. So you can see we have the drag chute that was added about halfway through the shuttle program. This drag chute in the back actually increases our stability on the runway. It helps prevent things like a blown tire, which we had a blown tire early in the shuttle days, and we don't want that to happen again. So let's see, what happened here? There we go. So we are readapting to being back on Earth, and I come out of the shuttle, come down the ladder, and we changed into our blue flight suits and we did a walk around. I'm going to talk about that later. And you have to go over and make a statement to the press, but really what you're saying in your head is, why are my feet stuck to the ground? Because really, once you get up in space, you know, we had a very, very important mission on Flight Day 1. It was to safely and successfully deploy Chandra. But on the other hand, it's hard for the human body to adapt to space. If you can think the first time you get on roller skates, or maybe the first time you got on a skateboard, you're kind of wobbly. That's what it's like when you get out of your seat for the first time. You know, things, you start bumping into things, you know, your pencils start floating away, there's dust in the air. You think you look down, then you look up and you're upside down, and how did I get here? You know, you just kind of float. And then your crew member's like, hey, you need to go down the stairs head first. Well, you don't want to do that on the first day because you can very likely make yourself sick. So we as a crew tried to be very, very careful on the first day to make sure that we didn't get ourselves physically or mentally disoriented because we had to get this very important mission off. And I'm happy to say that my crew adapted very well. We had procedures in place to make sure that we stayed focused on the primary mission of Chandra. I want to say one other thing, and then I guess we can take some questions if that's okay, if we have time for questions. So I try to avoid the ringing. We had a close call on this flight. We actually had 2 close calls. So this was the Columbia, which was the oldest orbiter. And Columbia had flown, I can't remember how many missions, but it had been through, in fact, Columbia flew the first flight back in 1981. So this had been flying for 18 years. 5 seconds after we lifted off, we had an electrical short. AC-1 Phase A bus just blipped for about 1 second. And when that happened, the crew got a light on our emergency panel, we got a master alarm, and we got a call from Houston that said, Columbia AC bus sensors off, which protects for the next failure. So my pilot did that, and I thought, honestly, for a minute I thought I was in the simulator, because you practice malfunctions in the simulator, but not on the real launch day. So we had the electrical short, and then my next thought was there's a lot of people back there in mission control that are really worried right now. But we continued on up. The other thing that happened is we had a leak, and the video goes pretty fast, but in our right engine, a pin popped out of an injector plate and it hit the cooling tubes in the nozzle of our right engine. And it opened up 3 of those cooling tubes, and we leaked hydrogen all the way to orbit. And we had what was called a LOX low-level cutoff. So although we were leaking hydrogen, because of the mixture ratio, we actually ran out of oxidizer, or LOX, liquid oxygen. And there's 4 sensors in that orange tank that when you run out of gas, those 4 sensors send a command to shut the engines down. And that's what happened on our flight. We had only 2 ever in the history of the shuttle program. Out of 135 flights, we had a LOX low-level cutoff. And so we knew that, and we thought, are we going to lose the mission? Are we going to have to bring Chandra back? And we did not want to bring Chandra back for obvious reasons. It's very expensive to take it up there, but it's also was the heaviest payload ever launched on the shuttle, and it would be a big challenge to land with that much weight on board. But fortunately, the shuttle has our OMS engines, which are our orbital engines, had enough, enough margin on the fuel to raise our altitude up to where it should be. And it was only a 15 foot per second underspeed, which, you know, I would say is kind of minor compared to the ones we practiced in the simulator, but it was still significant enough that we had to make an adjustment to our burns. But we did get Chandra off. And I say Columbia was the oldest orbiter. We eventually lost Columbia in an accident 4 years after this, which was, you know, we felt like the shuttle Columbia is almost like a family member. It was almost like a person, because the people that worked on Columbia had spent, you know, many of them their whole working lives with Columbia, as well as the scientists that had spent their whole working lives on Chandra and the technicians that had built it. So, you know, we take very, very good care of the hardware, but sometimes these things happen. So I thought I'd just share that with you, that we had a couple of close calls, but, and I will say that the flight controllers in Houston Mission Control manage those problems perfectly. You can actually go online if you want, and you can search for the Chandra launch STS-93, and you can listen to, it's on a YouTube video. Somebody put it out there. You can actually listen to what the flight controllers are saying, and I'll tell you, it makes your hair stand on end when you hear how they're talking about, you know, the tags are off, and, you know, they had lost data, so they weren't really sure of being able to diagnose what the problem was. They had lost data on the leak because of the electrical short. So it's a very interesting, I won't go into the situation more than that, but I will say, you know, I think back and I go, wow, you know, I wasn't even worried as we were heading up. You know, the crew was kind of blind to a lot of the problems that were happening, but there were a lot of people on the ground that were really worried that, and once we got the Chandra out, we were fine. So the mission actually went successful. And by the way, the shuttle program grounded all the shuttles after our flight, and all the wiring had to be inspected. And all the shuttles had to be, I guess there was a Hubble mission that was going up shortly after ours, and all of them had to be grounded, pull the panels to make sure that there weren't any more shorts. And I didn't mention this, but what happened, there was a wire bundle with a panel on top of it, and there was a screw head on that panel that was rubbing against the insulation on the wires, and the workers were walking over those panels, and that's why we ended up getting that problem. So that all had to be inspected. Oh, let's see, anything else? Well, you know, why don't I answer your questions? Because you probably have some other, I'm not a scientist. I want to say that I thought the briefing before ours was fantastic. And I look back 20 years ago that I was part of launching Chandra. I mean, what an amazing, amazing scientific discoveries that we've made in 20 years. I just feel so proud to be part of that, and it's great for me now to listen to our scientists and our researchers talk about all the things that we've learned from that mission. It was built for 5 years, and it's gone for 20. And I think, Rudy, I think you said it can go another 30 years or something like that. So we might be able to, kudos to the folks that built it. All right, well, can I answer any questions that anybody might have about not only what we did to deploy the Chandra, but maybe some questions on what it's like to be in space, or what's happening in the future. I mean, we're not flying the shuttle anymore, as you all know. It was shut down the program was shut down in 2011. The money that went into the space shuttle program was then earmarked towards building the replacements for the shuttle. That was 8 years ago, and we're still trying to build a replacement to the shuttle and get those launched. It goes to show you how hard it is to do human spaceflight. And we're hoping that we haven't launched astronauts out of Kennedy Space Center since 2011. And so one of our goals was to get, you know, it was supposed to be 2015, and here it is 2019. So hopefully in the next year or so, we'll start launching our astronauts again from Kennedy Space Center. Hopefully. Maybe Tracy will ask me a question.
I will, yes. Thank you so much. I am going to take microphone privilege and ask you the first question. Who won the contest of building the biggest water bubble on the space shuttle while you were up there?
I would say our Navy guy, because he liked to play with water. So that was Jeff. He practiced and practiced and practiced. So we used to say, you're just a Navy guy, you like to play with water. So we just wrote it off as that.
Okay, if we have questions, you can, yeah, go ahead.
So, very impressed with your accomplishments, and just want to ask you, being the first female shuttle commander, how did that feel? Did you get support, and how was the pressure?
Well, I always tell people I don't have feelings. How did it feel? No feelings, which is a joke, but you know, I'm asked that question a lot, and I think it was very important for me to focus on the mission and to not think about, like, to me, that was kind of a distraction, the first woman commander, the first female commander, and I remember we had our press conferences and they would fill the room up because everybody's like, what's the woman commander like? And I'm like, no, I'm just a commander. And so I think it was really important for us to stay focused on the mission. And I would tell my crew, I know there's going to be distractions because there's never been a woman commander, and you know, everybody wants to, you know, come and talk about that. You know, are you getting along with your crew, or how do they feel reporting to a woman? All I can say about that is the people I worked with were so professional. It doesn't matter whether you're working with a man or a woman or what the person looks like. When you all come to the table, it's what's the mission and what's my contribution to it, and how do we work together as a team? And you know, I really don't remember having any problems with that, because the people I worked with, not just my crew and the instructors and the flight controllers and, you know, scientists, technicians, managers, everybody was so excited about whatever the mission was. In this case, Chandra was so excited about getting the missions off and so focused on that that we really didn't think about, you know, what people look like or whether it was a man or a woman. So I was really grateful for working in an environment like that, and that was the environment I had at NASA. And I think that the women fit in really well. Not to say that everything was perfect. I mean, there's still, you know, you still run into issues out there. But I would say I loved it. I loved just being with the people. And when we did have to go meet the press, and they would ask questions about, you know, and a lot of them were kind of silly questions, and I got, you know, hit a couple times, you know, you shouldn't be like that, you should be this way. I don't let that stuff bother me. I know, you know, I'm out there because it's the taxpayers that pay for this hardware, they paid for the shuttle program, they pay for all the science experiments and all the telescopes, and it's our duty to talk to the public and tell them what we're doing and why it's important to them. And I mean, you take a look at these great things that we're learning about the universe that we live in. How can you not be excited about that? And there was just so much tremendous support. So, you know, I appreciate the question, and I tried to avoid the distractions. I try to stay focused on what is our mission and why are we here. And that's the advice I give to young people too. I appreciate the question, thanks.
So this is kind of a two-part question. First of all, was the T-38 your first fighter that you flew? And if it wasn't, what was before that as far as all the fighters, and which one was more difficult to fly and more nerve-wracking?
So I was an Air Force pilot and a test pilot before I went to NASA. So in pilot training, we flew the T-37, which was a jet, but it wasn't supersonic, and then we flew the T-38, which is the one that you saw here, which is a tandem. You had the student in the front, the instructor in the back, supersonic jet trainer. The Air Force still flies it, and honestly, it's probably one of my favorite airplanes because I just think they did a great job building it, and it's perfect for the mission that it does of training. I went on and I flew C-141s, which is a great big cargo airplane, and when I did my astronaut interview, you know, they always ask you the question like, well, what do you have to offer? What do you have to bring us? And you know, I told them I have something a little bit different. I was a C-141 pilot, and there weren't any astronauts that had flown a C-141. One astronaut, Dick Scobie, who was the Challenger commander, had flown C-5s. But other than that, the previous astronauts were all fighter pilots. So I talked about how the space shuttle mission is really more like a C-141 mission, where in the 141 you got two pilots, you know, a captain and a first officer. You got two flight engineers, you got loadmasters. Sometimes you have flight nurses, sometimes you have couriers, but very similar to what you have in the space shuttle program. So, you know, I try to use that angle, but it's also important to have the fighter time, because if you have fighter time, when you become an astronaut, you know that you can operate in that kind of environment, that you can think and you can fly and you can make decisions, make judgments while you're under a lot of stress, a lot of physical as well as mental stress, flying in a fighter. When I was at the Air Force Test Pilot School, I got to fly 30 different types of aircraft. So I'm going to tell you, it's maybe a little bit boring, but my favorite plane was the A-7, which is an older plane. The Navy flew it quite a bit. It's not supersonic, but it had one engine, but one seat. The first time you fly it, you go solo. So you just have to pass a written test, and they give you the keys, and off you go. So I got to fly that, and we flew the F-15, the F-16, a lot of the fighters. Back in those days, women were not allowed to fly fighters. So it was 1993 when the United States allowed women to fly combat missions, and then the Air Force and the Navy started checking women out in combat aircraft, 1993. So prior to that, women could fly cargo, and fly as instructors, or fly tankers, which do the air refueling, or they could fly the administrative aircraft, but no fighters or bombers. Well, again, that changed in 1993. And by the way, it was 1976 when women were first allowed to fly in the military. So it wasn't always that way. So things have changed. A lot of young people don't know that. But I hope I answered your question. I think, you know, today we've got these, you know, the F-35, the F-22, they're like flying computers. And it's a lot different. You know, back in the old days, it was a lot more stick and rudder. But I haven't flown the F-35. I'm definitely not knocking it. I think it's a great airplane. So, have another question there?
Yeah. So you said that y'all spent 10 days in isolation before. Yes. So what did y'all do as far, or like medically, to like strengthen your immune system before or during that time period in preparation?
Yeah, okay, so the astronauts have, good question, there's 7 days of required, what we call quarantine, and you spend 3 of those days in the quarantine facility at Johnson Space Center, then you fly the T-38 down, you one hop it down to Kennedy Space Center. Can't stop and get gas because then you get exposed to but you fly straight down to Kennedy Space Center, you spend 4 days. Well, the reason we were 10 days is we had launch delays. So to answer your question, we have meetings. We can really only be exposed to a few people, like the cooks. Some of our instructors can come in. But we're pretty much on our own, going through procedures, holding meetings as a crew, going over the flight plan. We're staying busy. But the other thing we do in quarantine is we're sleep shifting. So we had a 12-hour sleep shift. So I'm trying to remember what time we woke up. I think we were waking up at like 7 p.m. at night. So to do the sleep shift, we stay up later every day. You go under bright lights, because there's what they call a prescription. You sit under bright lights. So the first night, I think we stayed up till like 3 a.m. in the morning, watching movies under the bright lights. And then you go to bed and you sleep 9 hours. And so we keep sleep shifting until we get on the schedule that we need to be for the mission. So that happens in quarantine. You also can't eat food from outside. You only can eat the cook's food because they don't want you to get sick on food. And if a crew member gets sick, like if you get a head cold, you're going to have a terrible time in space, because when you're up in space, you get a fluid shift and your whole head gets like overhydrated, and your legs get skinny, which is, it's a little kind of I would say a side effect. But you don't want to go up in space with a cold, because you're going to be very miserable. So we try to, prevent. It's not 100% effective, but I think I know one time an astronaut got sick in quarantine. But for the most part, it keeps us from getting sick so we can launch on time. Let's see, well, I was going to say one other thing about quarantine. This particular mission, we had 2 launch scrubs. And the first one was due to a sensor. I think it was T-minus 8 seconds. A controller in Kennedy Space Center Launch Control saw a hydrogen sensor in the aft compartment of the orbiter jump. And he thought that there was a hydrogen leak, which would be extremely explosive. He stopped the launch. There's only a few people that have their hand on the button that can stop a launch. And when he stopped the launch, before the engine started, it was a 2-day delay. So we got out, went back to quarantine. 2 days later, we get back in the orbiter. The weatherman told us, you have a 100% chance of good weather tonight. And we'd go out to launch, and we scrubbed for thunderstorms. So the weatherman said, I will never again say there's a 100% chance of good weather. So we went back again the third night, and we launched the third night. And by the way, it was getting very close to the end of a launch window for Chandra. Our launch window was 40 minutes, and it was all based on Chandra's orbit. And if we took many more delays, we were going to have to wait like a month or 2 before we could try to launch again. How are we doing on time?
I think we're going to have to wrap up right here.
Okay. I'll stay as long
let's
as you
give a
want.
big round of applause. Let's also please thank again Dr. Rodolfo Montez for his amazing talk earlier as well. And before we completely wrap up, on those pieces of paper you guys have on your chairs on the backside, it's a big thank you to all of our sponsors, but also a survey. We'd love to hear what you guys thought about tonight's event. Don't forget to come out next Wednesday. And on behalf of Astronomy on Tap,
We thank you. Have a good night, guys.
thanks everyone.
That's it? That's the last one?
I think that's it. I think we're good. Good job, Adam. Good job. To my knowledge, there's still beer outside. We encourage you to drink it if you're not driving. Please go get it if you're not driving. They will close at 9 though. Got 10 minutes.